We will here talk about the geometric representation of the trigonometry expressions, and the trigonometry expressions we have to write in these ways, where we need to follow the spreadsheet style of writing of the trigonometry expressions. Every student should know how to write the expressions in any softwares to get the help of the softwares. If we don't know how to ride bicycle, then we cannot get the benefit of bicycle, and no one is going to give you any certificate for the bicycling. But it is for our own need that we need to know how to use bicycle. And in the same way here, to get the help of the softwares, we should know how to encode any formula in any software, like in any spreadsheet. We need to know how to encode this formula into the spreadsheet cells. If we don't know the art of writing this formula in spreadsheet cells, then we cannot get the benefit from any softwares. And for writing this kind of formula, no one is going to give you any certificate, but these are done to get the benefits. Now we will start how to think about the geometrifying trigonometry and encoding of the school level formulas or college level formulas into the expressions. And geometrifying trigonometry has its own language to encode and decode the geometric interpretation of the trigonometry expressions. First of all, here we are talking about the Indian Board of the Trigonometry Expressions database, the master database, and from the Sanjoy Nath'S Geometrifying Trigonometry, parsing to construct the trigonometry expressions, the well-formed formula, the WFF. Well-formed formula means the way we should encode the formula into the spreadsheet-like softwares. And the bracket balancing is very important. The bracket balancing means writing the formula in such a way that the bracket enclosing are completed. And here you can see that the red colors are the balanced brackets, and the end of the formula is having another bracket balancing, that is the first bracket is ended somewhere, and every bracket has its own pair, and this pairing of these brackets are very important while encoding the formula into the spreadsheet like softwares. If you miss any bracket, then there are the chances of the errors and you will not get the outputs. And this habit is very important to get the benefits from the modern softwares. And in Sanjoy Nath'S Geometrifying Trigonometry, 1 is treated as the L, that is the initial line segment. Okay, and every time the parser will convert any one kind of things into the L star. Whenever geometrifying trigonometry finds there is a 1 star, that means it is considered as the L star. L star means the whole operation started from the initial line segment L on the tracing papers. Now a little glimpse about the theory and the parsing mechanisms is discussed here. In Sanjoy Nath'S Geometrifying Trigonometry, each GT simplex, that is the multiplicative forms, are described with the initial line segment L and the final line segment Z. Suppose in the simulator we can see that every GT simplex starts with L and ends with Z. Another, in this way we write it. If we want to see the moon and star combinations, then we will use the Z. That is the multiplication of cos theta and sec theta is repeatedly done, and in the output summation cases we get a complete circle here for the theta is equal to 11.8 degree. And if we take another bunch of line segments, that is the GT simplex, and if we consider it as the L there is the cos theta sec theta combination. It starts with L and ends with Z, and in this way we will get the moon and star combination here. That is, for the different theta we are getting the different kinds of moons and different kinds of stars, and in the complement also we are getting the different kind of behaviors of the moon star duplets, the moon star dualities. The moon and the star are the two dualities of the 1 means cos theta into sec theta multiplied continuously in the contiguously. They forms this kind of moon star combinations, and one moon and one star in the summation of the series is like this: L LA LAO LAOA LAOAO. In this way the moon is constructed, and LB LBBP LBBPPB LPPBP. In this way, if we continue, then the moon star combinations are constructed. Now we return back to the encoding of these formulas and the art of parsing of such things. Say each of these GT simplexes are starting with the L, then the operators A to Z are used, and it completes the Z. That means the complete GT simplex, the multiplicative form is completed, and sequence is a separate GT simplex for the different bunches that L starts with the L and ends with the Z. Here is the command to encode the trigonometry expressions, where A, B, C, D means cos theta, the four symmetries of cos theta. E, F, G, H are four symmetries of sin theta, and on the GT simplex, the geometrifying trigonometry, multi-GT simplex comparing simulator version 17. In Sanjoy Nath'S system, we can see here that it is already written on the screen that L is the initial line segment and Z is the final output line segment for every GT simplexes, and the operators cos means A, B, C, D are the four different construction protocols for the cos. For E, F, G, H are four construction protocols for the sine. I, J, K, M are the four construction protocol for tan. N, O, P, Q are four construction protocol for sec. R, S, T, U are four construction protocols for cosec theta, and V, W, X, Y are the four construction protocols for cot theta, and all of these are considered on the 2D Euclidean geometry plane. Now again we are coming back to the theory descriptions here. A little bit theory is described here so that people can understand how to think and how to use about these kind of softwares here. Now each GT simplex starts fresh from the initial line segment L. The GT simplex are the multiplicative forms, like here in the simulator we have shown that the cos theta is cos multiplied with sec theta, again it is multiplied with cos theta, again it is multiplied with sec theta. In this way we can construct the multiple symmetries, and we can generate the different kind of geometric options, and we can think about the very deeper kind of theories, very deeper kind of theorems, very deeper kind of different kind of calculus and the summation of the series, and we can think on these kind of things, and we can intuitionally understand the geometric natures of the things, and such that we can find different kind of summation formulas from these geometrifying trigonometry understanding on the trigonometry expressions. Now when we are talking about the GT simplexes, that means purely multiplied forms of the multiple trigonometry ratios with the different kind of theta, and the theta can vary and theta can remain same, but when the summation of the series are done, then we can get different kind of perimetry, and we can get the different kind of curves, and curve construction systems are there. So a new kind of calculus is encoded with geometrifying trigonometry systems. Now in Sanjoy Nath'S geometrifying trigonometry system, some conventions are followed, and each GT simplex has its own summation curves from the origin, and all GT simplex triangles rendered together in the union visualizations is shown as the tracing papers are kept one after another, one above another, with the aligned L and the stacked tracing paper. From the top view we can see these kind of images that you are seeing on the GT simplex simulators, and it is easier to simulate with the softwares, and so we are using the softwares here. And software is not to show the software here, the software is here to make you understand about the theory of the geometrifying trigonometry. All summation curves are rendered together, and the comparisons are done for the visualization purposes, and it is going to save you time, and it is going to give you the intuitions about the geometric natures of the trigonometry expressions. Example: LAOZ, LBCZ, LEFZ creates the three independent GT simplex, and whereas for the new systems will generate an all permuted with the Cartesian product, the GT strings. These are all the strings that we are talking about here, and the what we have shown here on the simulator screen here. These kind of things are called the GT strings, and the GT simplex strings is a better term to use. The GT string objects and all rearranged GT strings are then handled with the Cartesian products and options and generators, and which find and replace the cos equivalence constructions protocols and ABCD, which find and replace with the sine equivalent construction protocols EFGH, and find replaces of the tan equivalence construction protocols of the IJKM. In this way, with the find and replace of the sec equivalent construction protocols with the NOPQ, and with the systems in which find and replace or the for the cosec equivalent construction protocols RSTU, and with the find and replace or the copy and of the construction equivalents of the cot. Here it is the cot. Cot means not just a ratio, and any of these things are not just the ratio, they are the construction protocols on the 2D Euclidean plane. And these construction protocols for the cot are the VWXY. These are covering all of these are covering the four symmetries for the construction protocols on the 2D Euclidean plane for every of the trigonometry ratios, and such that we can automatically generate the geometries from these things. Now cos squared theta means all of the 16 options together. How can we think about these all of these 16 options together? Suppose here if we write only one option of these representatives, say LAAZ, and if we want to get all the permutations and the Cartesian products, then we will generate all the things, and then we will see that 16 options are all constructed, that is LAAZ, LABZ, LACZ, LADZ, LBAZ, LBBZ, LBCZ, LBDZ, LCAZ, CBZ, CCZ, CDZ, DAZ, DBZ, DCZ, DDZ, and when we will select all and we will load all, then we will see that all of these tracing papers of the 16 tracing papers are stacked one after another, and from the top view we will get this kind of images for the varying values of the theta. This is the thing that we were talking about here, and we are describing the things here so that we can understand the things we have shown in the visualizations and the model of our working. Now cos squared theta means all the 16 options, that's the Cartesian products, and which I have already explained on the simulator now, and the visualizations is also shown here, the multiple tracing papers stacked one above another, and we were varying the theta to get the understanding of the varied forms of the 16 tracing paper stacks every time, and such that from the top view we were seeing the different kind of images that were constructed there. Now GT simplex, its LAOZ starts with the initial L and own summations, and GT simplex 2 LBCZ also starts with the same L and own summation, LEFZ, and starts from the same initial line segment L and the own summation, and all of these things are coming on the different tracing paper sets. And from the stack of the tracing paper sets we were seeing the images that we are showing in the simulator window. Here the different panels are there. The first panel, the left side panel, is showing the GT simplex objects. The second panel, the output summations, only the output line segments taken and kept them like the vectors, one above another, and that is the toe tip combinations. And similarly, if we keep the complement line segments only, and if we place them in the toe tip variation way of the summation, then we will get this kind of pictures. And from the cos square theta variations, we can see the choreography of this cos square theta. For the theta varying from the 0 to 360 degree, we can see that the characters are dancing. We can see the things like this, and we can design different kind of choreography of the character animations with the trigonometry encoding systems on the Geometrifying Trigonometry simulator windows, and with that is important things. And then we can export those things to the Poser Pro or the DXF or to other kind of softwares to work with our crystallography or with the choreography and whatever we want to use for these kind of things. But it is a new kind of calculus, it's a new kind of mathematics with which we can encode and decode the geometry and the trigonometry expressions and interoperate with between these two kind of things. Now Pythagoras also tried to do these kind of things to relate the geometric objects with triangles, intermediate things, and then converting the insights to the numbers, and the properties of the numbers are related with the properties of the triangles, and the properties of the triangles are related with the properties of geometries. In this way, the Pythagoras theorem is all pervasive, and it is working for any kind of engineering and the other kind of practical uses. And even today, and Pythagoras has never claimed for the patent for these kind of things, but if he would got the patent, then he would become a trillionaire. So now we are trying to generate the separate PDF files also with the 4 boxes instead of the only 2 boxes, and we need the cumulative summations for all the complements, line segments also, and every triangle constructions, and every operators construct the 2 line segments from the given line segment. One is the output line segment and the other is the complement line segment, and this way we get the 3 line segments from the triangle constructions, and all these line segments have the orientations. Now the initial line segment L or any given line segment is there for any kind of gluing. We are consuming one line segment segment and constructing two other line segments. One is the output line segment and another is the complement line segment. So the given line segment, output line segment and the complement line segment, these three line segments are constructing a complete triangle for any such cases, and these triangles are the real numbers and all the real numbers are the triangles in the Sanjoy Nath'S geometrifying trigonometry. And in this way, for every real numbers we first encode it as a triangle, and the calipering and the division operations construct these triangles, and after the triangles are constructed, the multiplication is used to the gluing of these triangles, and after the gluings are done we get the GT simplexes. And for every GT simplexes, every GT simplexes starts from the single common L, that is the L is the given line segment for the all the kind of GT simplexes that whatever we are comparing or constructing, and we stack one GT simplex above another on the different tracing papers. And when we look at the bunch of the tracing papers from the top view, we get the whole pictures together, and for the varying values of the thetas, these values of these pictures of the GT simplexes changes, and then we can compare with the multiple scenarios of the GT simplexes, and with that we get the deeper understandings about the relatedness between the numbers, properties of the numbers and properties of the GT simplexes, the properties of the numbers and properties of the triangles. Pythagoras was working only with the right angle triangles, but Sanjoy Nath'S Geometrifying Trigonometry is trying to encode with the many kind of GT simplexes and many kind of graph theory like objects, and they are related with the properties of the equations and properties of the numbers, and in this way we can get the deeper insights of the quantum physics also. Now the three line segments of the triangle construction, all these line segments have the orientations, and for every different kinds of the orientations we get different kinds of the cumulative summations. And in Sanjoy Nath'S Geometrifying Trigonometry is the exhaustive trigonometry, and which is far ahead of the ordinary trigonometry, and we need to become more cautious to construct the theorems for such exhaustive and deep trigonometry cases, and we cannot cut short for the purposes to save the tokens, in which we as the artificial intelligence worlds are doing right now. So Sanjoy Nath'S Geometrifying Trigonometry is not to save the tokens, it is to give you the exhaustive case studies of all the kind of expressions and such that you can think about the deeper natures of the theorems and their interrelatedness between the properties of the numbers, the properties of the equations, and the properties of the hidden geometries inside the cases. And all the exhaustive geometries are examined together such that we can understand the nature of the behaviors of every equations, geometrically interacting line segments and what they are going to do. These line segments are not only the line segments, these are the lines of forces also. And if we can think these are the free body diagrams, or the way the truss or the other structural components are interacting with the force diagrams, and then we can visualize the whole things as the trigonometry expressions. And these are the important aspects of the Sanjoy Nath'S Geometrifying Trigonometry. And all projects need to write such that helping text prepared repeatedly with the small fonts and the sizes. And this when the a theta expressions, the sign expressions like plus theta, the hard coded a theta expressions arithmetic, if we omit the a theta and write a only, then it is to consider that a as the a theta, and the theta is iterated, and that takes the different defaults and for the things to do. And for all other alphabet protocols also, for example, simply writing b means considering it as the b theta until and unless the b theta expression is written there. And similarly it is for the c means c theta, d means d theta, e means e theta, and we have to write the things in this way. And if we don't write the complete things, if we omit the term theta, then the GT simplex simulator will automatically encode the theta there, and this theta is the varying parameters and with which we can simulate the whole things. So it is not always mandatory to write the theta every time, because the software takes care about the things such that the students can play with the software and they can find the different deeper insights about the realities of the geometric ways of understanding the trigonometry expressions. And that is the first motive to do with the work with the Sanjoy Nath'S Geometrifying Trigonometry. And after that there are the different crystallographic needs, architectural needs, surveying map needs, and several business use cases are also there due to this. But at least the students should get the understanding of the geometric patterns that are hidden inside the trigonometry expressions and how these patterns vary when theta is changing. Now these arithmetic things and things are evaluated first, and the geometry calculations degrees. And suppose when the expressions are evaluated, when the things are inside the trigonometry expression, suppose some theta expressions can have any mathematical formula over there, then we will parse it to the numerical values, and these numerical values are nothing but the values in the degrees or the radians. And whenever these expressions are outside these theta expressions, like suppose the theta expression is not inside the cos bracket, if the theta expression is not inside the sine, tan, cosec, sec, cot, inverse, these kind of bracketed things, then we will not evaluate it first. We will consider the geometry in those cases. But if those theta expressions are inside any trigonometry expressions, then we will evaluate it as a pure number. We will not use our geometry kind of parsing there for those kind of cases. This is the strict cautions that we are trying to explain over here. And the arithmetic things are on these plus minus into divide things are evaluated first when those are as a theta expressions. But if the theta expression things are pure num and calculations are not done for those theta expression cases, if those are out of the trigonometry expression cases, and on those cases the simple arithmetic equation evaluation systems within the theta expressions parts are not allowed for the other kind of cases. For example, suppose we are working with this kind of cases where the theta kind of things which can have the numerical values, but when the things are not inside the cos or sine or kind of things, suppose this plus, it is outside this theta expression kind of thing, so here we will not parse this plus as the numerical value. We will not consider this kind of multiplication as the numerical value. We will consider these things as a geometric construction protocol. This is the thing that we were trying to say here. Now, after discussing these points, now we will enter here with the concepts like the tracing papers understanding. The whole system's constructability are checked for what domain of that evaluations and the constructions are possible, and then the current code considers only up to 0 to 90 degrees, and now we have extended it to the 0 to 360 degree in the version 17. The previous code in the version 15 that was working only up to 0 to 90 degree. Now our system is extended to the 0 to 360 degree simulation systems, and we need to extend these to the 4 quadrant 360 degrees in the coverages and are necessary to handle, and these things are done. And here we have the robust level of the godly way of the doing geometry, where all the possible cases are handled, and all pages need to write such helping text repeatedly with the small fonts, and that automatically coming now with the PDF generations with the iterations. Now all real numbers are the 4 star 4 16 types of the triangles interpretations, and to prove this fact we can say easily that all real numbers are classified in the 3 categories. The first category is the pure fractional number, which are between the -1 and +1, and we can write these numbers in the 4 types of the pure fractional number, 4 types of triangle involvements as a cos or sine or tan or cot, and any kind of pure fractional numbers are written in these 4 ways. Similarly, these all have the 4 symmetries that we have already discussed, that A, B, C, D, E, F, G, H in that way, and we have already discussed the 4 types of symmetries, and we have and A, B, C, D for the cos, E, F, G, H for the sine, I, J, K, M for the tan, and these are the symmetry constructions on the 2D Euclidean plane, and A, N, O, P, Q for the sec, R, S, T, U for the cosec, and V, W, X, Y, R for the cot, and these are all Sanjoy Nath'S terminology used in the Sanjoy Nath'S Geometrifying Trigonometry. These construction protocols have their own algorithms, and with these algorithms, and you can test these algorithms on the pen and paper yourself, and you don't have to use the software to test these algorithms. You can check with your pen and paper physically. This software is just to help you to understand and to think about the theorems more deeply, more easily, more with the simulation systems, and you can test with these things, and you can also write the books with the multiple varieties of the theta. And this software is for helping, like cycle is going to help you to comfortably move from one place to another, but you can walk also. In the same way, in the trigonometry you can do the geometrifying trigonometry without the software also, but with the software you can do it easily. In that way we are trying to say here. The software is not the first thing to talk about. The theory and the encoding systems and the decoding systems is the fundamental thing that you have to understand first. Now, here we can see that we have documented this detail in a elaborative way such that you can understand what we are trying to talk about. Now, all these alphabets are actually the construction protocols, and with these alphabets we will discuss about the trigonometry expressions that we have written here. Sanjoy Nath has arranged 6,800 school level trigonometry expressions, college level trigonometry expressions, math olympiad level trigonometry expressions also, such that we can discuss about these trigonometric expressions with the geometric facts and understanding. Suppose here the trigonometry expressions is there, and which we can think about the cosec theta star cosec theta minus cot theta star cot theta, that it is the bracket balanced way of writing, and this is the art of writing for the spreadsheet way of writing the formulas. In this way, wherever the one star is there, there is nothing is written, that is the one star is there, and one star means the L star. It is the game should start from the initial line segment. Here the red colored brackets are showing you the bracket balancing conventions. The red colors are the bracket pairing. Here whenever we are clicking over the bracket and it is red colored to the pair, in this way we can understand how the brackets are balanced. The bracket balancing is the first thing that we have to do. We have to think while writing the well-formed formula. Well-formed formula means all the brackets are balanced first, and after understanding the bracket balancing, then we have to understand where the one is missing. If the one is missing, then we have to type the one star there. If we don't write the one star there, then any spreadsheet will automatically consider the one star is present there. One star is there, and geometrifying trigonometry will automatically assume that the L star is there, because the game starts with the initial line segment L, and that is the first thing that some geometrifying trigonometry simulators do. Is it takes the it consumes the trigonometry expressions in this way, and wherever the one is missing, it is first going to put the one star there, and when the one star is there, geometrifying trigonometry simulator converts it to the L star, means the game starts with the initial line segment L every time, and whenever there is only one is there, then geometrifying trigonometry simulator will consider it as the L. That means if left hand side expression is generating something, and if the right hand side expression is generating something, if the left hand side expression is generating some line segment output Z, and the right side expression is generating the exact overlapped line segment L over there, then that means it is the exactly returning on the same line segment. Suppose LABZ is generating some line segment, and when theta is changing, you can see that LABZ is exactly overlapping over the L, and it is a partial part of this whole L. Okay, in a similar way, if we talk about the LEFZ, then the EFZ is not overlapping on the L. So if we think about the LEGZ, say LEGZ, then EGZ is overlapping on the Z, on the L, but it is on the different side. So say if it is the LEHZ, then also it is not overlapping on the L. EZ, EFZ, EG, EF is not overlapping, EG is not overlapping, EH is not overlapping, EE is not overlapping but parallel. In the same way, if we consider LFE, FF, FG, FH, GE, GF, GG, GH, HE, HF, HG, HH, then we can see that HH is overlapping and on the opposite side, and if we take these one after another, then the total L will come out, and LABZ and LHHZ are overlapping and end to end feet. In the same way, EE or EH, we can see that LEH is generating the line segment, which is exactly overlapping on the L and which is end to end fit with the LABZ, and for every values of theta we want to check this process is working or not. Here we can see that LABZ and LEHZ are exactly overlapping on L. Here the L line segment is there, and LAB and LEH are exactly overlapping with each other, and we want to see that the complement line segments are behaving in this way, and we can see that the complementary line segment summations construct a complete polygon here at the 45-degree angle. This is interesting subject here. LABZ and LEHZ we can examine with the LBAZ and LHEZ. We have found that LBAZ is overlapping but LHEZ is not overlapping. GF, H, G, HZ, HGZ is overlapping, and we can see that for HGZ we can see the choreography of this bunch of line segments and the Pythagoras theory, where the L is exactly overlapping on the summation of these two line segments. And these are the kind of theories which we can think about, and we can search for these kind of images, and we can test that in which other physical cases these kind of images are applicable, and it can be used in the quantum mechanics or in some other crystallography things. And we need to search for these kind of images where these kind of images are also commonly visible, and this kind of understanding is going to give us a deeper understanding about the relationships between the properties of the number, the properties of the equations, and the properties of the geometries on the 2D Euclidean plane. This is the power of Sanjoy Nath'S geometrifying trigonometry. If Pythagoras had to claim for patent, he could claim for all such images and all such configurations for which the industry would pay. In the new capitalistic structures, Pythagoras could become rich. We will talk about the Pythagoras theorem, and if Pythagoras had to ask for patent or for the royalty, then he could get a lot of money and his family could become rich. Pythagoras was interested to talk everything with the geometry and relating it with the numbers. In Sanjoy Nath'S Geometrifying Trigonometry, Sanjoy Nath extends the Pythagorean way of philosophy to the concept that all real numbers are actually triangles. Those triangles are drawn on the 2D Euclidean plane, and all 2D Euclidean triangles are real numbers, and both these are true. To implement Sanjoy Nath'S geometrifying trigonometry on all our school days problems, or for the college days problems, or for the math olympiad problems, or for the IIT JEE, or any kind of trigonometry problems, we first have to write these things in the well-formed formula format, that is for the spreadsheet like formula, such that it is a formal language to represent the mathematical expressions. Students should know and understand that whenever there is a word kind of thing written like the 1, then we have to understand it as the initial line segment L. We start all our games with the initial given line segment L, and then we draw that same length L with the same kind of proportions on several tracing papers, and we will stack all these tracing papers one above another, such that we can see the top view and we can see the geometry alignments which are constructed on the basis of this L. Whenever we see these kind of expressions, then we should understand that 1 star sine theta means it should be written as the L star sine theta plus L star cos theta. That means it's the Pythagorean theorem. And here this plus is a very dicey thing, it's a doubt kind of things, and because all the kind of output line segments generated from these L sin theta star sin theta are not always guaranteed that they are collinear and end-to-end fit with all other line segments constructed from the L star cos theta. That means L star sin theta will generate 16 types of symmetries on the 2D Euclidean plane, and we will get 16 tracing papers for these. Similarly, for L star cos theta, this kind of things, we will get 16 different other symmetries, and these symmetries, all of these 32 symmetries, are superimposed one above another, and then we will check this plus it is addable or not. That means which of these line segments which are constructed due to this L sin theta star sin theta are collinear and end-to-end fit with the line segments of the L star cos theta, and these well-formed formula kind of things are written in that way. And here we are seeing that on the right hand side there is a RHS, which means 1 and which is actually understood as L, that is the overlapping with the L. First of all, we will discuss on these kind of things. Here L sin theta star sin theta, which has a representative as the LEEZ, and for L cos theta star cos theta we have another representative, one such representative as the LAZ, and there are 16 types of such representatives for the L cos theta star cos theta. Let's look at the version 17 software of Sanjoy Nath'S Geometrifying Trigonometry, from where we will understand the real pictures very easily. Say LAAZ, and here L is this L, this is the given line segment on a tracing paper, and when we are drawing LA, then one line segment is constructed, then again A is multiplied, then another line segment is constructed, and the triangles are glued. And here we have already discussed one point, that is in Sanjoy Nath'S Geometrifying Trigonometry we use the bracket balancing models of writing of the things, and this multiplicative part is the GT simplex 1, and this multiplicative part is another GT simplex, the GT simplex 2. These two GT simplexes are interacting and then constructing the decision problems. Now we use the BOCDMS, BOCDMAS, it is not the BODMAS. First, the bracket balancing syntaxes of the well-formed formulas are written, and then we do the calipering. Calipering is the art of constructing the triangles from the real numbers, or to do the construction of the real numbers from the 2D triangles. And to construct the real numbers from 2D triangles, we have to do the calipering. And in the similar way, when we are trying to construct from the real numbers, then we have to do the calipering. This calipering is the straightening method, the sequential straightening method that we used to do from the ancient times for the involute constructions or the evolute constructions, and find the perimeter of any curves. In these kind of things, stage wise we used to straighten the wires, the thin wires we used to straighten slowly and steadily, and one after another pieces we used to align with the next piece, and in this way we used to unfold the whole curve, and then we used to do the straightening of the curve to construct the line segment. And this is a common way of finding the length of the curve. These problems were known from the ancient times, and this way we unfold any triangle, this way we unfold any polygon, in this way we unfold any graph, that is the G free E objects, the Eulerian graphs or the Hamiltonian graphs, or these any kind of graphs where the vertices and edges are there, where we unlock the vertices and then straighten the edges, and in this way the whole graph turns into a single line segment. And this is the art of the calipering, and we have separate videos on these calipering processes where we construct the triangle objects from the divisions operations. Divisions is the first fundamental operations after doing the calipering, and calipering of the geometric operations that is very much necessary to construct the triangles or deconstruct the triangles. Ultimately, this calipering is the fundamental operations after bracketing of the bracket balancing of the syntaxes are done, and after doing the calipering we can do the divisions. Divisions mean, in Sanjoy Nath'S Geometrifying Trigonometry, divisions mean constructions of the triangles from the two given line segments, and we can construct 4 different kind of triangles from the numerator line segment and the denominator line segment. Any expressions on the numerator side is also representing a line segment even after doing the calipering, and the denominator is also representing another line segment. And for every line segment there are the two ends. There is the start end and the end, that is the final end. There are four such combinations possible with the denominator line segment and with the numerator line segment. For example, for the division, when we see the denominator has the two end points, the start point of denominator and end point of denominator, the start point of numerator and end point of numerator. When we lift and shift the denominator line segment on the numerator line segment in such a way that the start point of the denominator line segment is placed on the start point of the numerator line segment, and then we get a caliper object which has the two edges which are attached with a single point, and then we connect the third line segment to complete the triangle, and this third line segment is the complement line segment actually. In this way we can arrange the start finish, finish start, finish finish. In this way we can construct four different orientations, four different arrangements for the triangles. And division operations in Sanjoy Nath'S Geometrifying Trigonometry is actually converting any ratio objects to the triangle objects, and any irrational numbers are also the ratio objects, because irrational number divided by 1 is also a kind of considerations to construct the triangles, and 1 is always considered as the L. L is the initial line segment in Sanjoy Nath'S Geometrifying Trigonometry. And multiplication is gluing in our software simulation version 17, in Sanjoy Nath'S Geometrifying Trigonometry version 17 in this software, while we are showing that how the gluing is working. Here I again demonstrate you that when L was there, then it was nothing, then L A is done, then one triangle is constructed, another A is done on that, then another triangle is glued to it, another A is there added, then in that way we see that another triangle is glued. In this way we get the Pythagoras spiral. In the similar way, Sanjoy Nath is extending this whole thing to the other kind of spiraling. Here LAB, this is also a variety of the cos square theta. LAA is a variety of cos square theta. LAB is also a variety of cos square theta. LAC is also a variety of the cos square theta. LAD is also a variety of cos square theta. In any kind of cos square theta, we can see the triangles are getting glued and one common edge is there, and the addresses are written beside the line segments on the GT simplex panel. Here you can see the two triangles are getting glued, and when we are doing the LAA, then the angles are added, and when we do the AB, these symmetry constructions, then the angles are not added, the same triangles are getting overlapped one another. And here in the GT simplex you can see that the LAB ultimately generates the line segment which is exactly overlapping on the L. Here we can see that LABZ, and in the same way if we do LBAZ, then we can see that LABZ and LBAZ both are constructing the final output line segments which are exactly overlapping over the L. We cannot guarantee that every time we will get this kind of cos square theta, and here if we see that LCDZ, then we see the LCDZ is constructed in this way, LCCZ is constructed in this way, LDCZ is going to construct the output line segments in this way. LCDZ and LDCZ are parallel to each other. Whatever the theta are constructed, they are parallel to L, and we can generate these kind of theorems here, and it is also a deeper theorem like the Pythagorean theorem. In the same way we can say here LACZ and LCAZ, then we can see that LACZ is parallel to LCAZ, and obviously the length of the LACZ and LCAZ are same, and these two final output line segments are always parallel, and when they cut for any angle, when this cut the L, then it will cut at the midpoint of the L. LACZ always cut the original initial line segment L at its midpoint, and this is another theorem from Sanjoy Nath'S Geometrifying Trigonometry. And in this way LCDZ, LCCZ And here we can see that LCCZ has a specific property where we can see that LCCZ and LACZ both are collinear and also overlapping for certain values of the theta, and sometimes they get detached, but they always remain collinear. This is another theorem from Sanjoy Nath'S Geometrifying Trigonometry. These are the choreography of the line segments and the choreography of the bunch of line segments, and these kind of theorems are deeper theorems than Pythagorean theorems, and because these kind of theorems were never exposed before the Sanjoy Nath'S Geometrifying Trigonometry conventions of the construction protocols were designed. For four symmetry, for everything are there. For Sanjoy Nath'S Geometrifying Trigonometry, the convention is followed as the L is the initial line segment, Z is the final line segment. Cos theta has the four symmetries A, B, C, D. Sin theta has four symmetries E, F, G, H. Tan theta has four symmetries I, J, K, M. Sec theta has four symmetries N, O, P, Q. Cosec theta has four symmetries R, S, T, U. Cot theta has four symmetries V, W, X, Y. Now, how many possible symmetries are there for the Cartesian products of the cos square theta? We can easily say that the cos square theta means ABCD Cartesian product with the ABCD. Then we will get AAAB BABB CACB and DADB Here we can write it in this way: LAAZ, LABZ, LACZ, LADZ. In this way we can construct all these symmetries and all these parameters, and from here we can find several deeper theorems. Due to the different values of the theta, we can understand the geometric natures are changing, and there is the choreography of the bunch of line segments we can see here. Now in the same way we can list all the permutations and the Cartesian products for this, and then we will see there are 16 possible varieties. Those are LAAZ, LABZ, LACZ, LADZ. Similarly, LBAZ, LBBZ, LBCZ, LBDZ, LCAZ, LCBZ, LCCZ, LCDZ, LDAZ, LDBZ, LDCZ, LDDZ. When we will select all and load all, we will see the choreography of the cos square theta, and those are the bunch of line segments. And if we place the tracing papers one above another, if we place the 16 tracing papers which are all constructed from the same L, and if we stack all these tracing papers one above another, then we can see the geometry of this cos square theta like things. And when we will search such things in internet, and then we understand these kind of geometries are talking about the deeper understanding about the theorems, and several use cases of such theorems are there. Say LAAZ and other permutes. Then if we go to Google and if we search for the Google search, and if we search with our image searches, say if we search with the images here, then we see the conditions like these. Say the 16 symmetries of the cos square theta. We can see the things, the GT simplex software applications which is appear to the tool of the mathematical geometry analysis, like to the structure in the creativity coding, and GT simplex triangles and multi-GT simplex commands, permutation selectors. And these kind of images are visible for other kind of softwares also, and we can see these are the crystallographic softwares where we can see these kind of images are present, and these kind of images are present in the applications of the magnetographies and material sciences, also in the maths Olympiad problems also. Even these kind of subjects, and where the design analysis of the rigid elastic coupling in the origami systems, and where also these kind of mathematical symmetries are used, And so there is a huge business for the Sanjoy Nath'S Geometrifying Trigonometry options, and because these theorems can save a lot of time, and after doing the reverse machine learning on these subjects, we can generate several such theorems where we can use very less number of tokens to generate many more number of insights. Now, if we consider the sine square theta part also, say we will write only two representatives here in the version 17 of Sanjoy Nath'S Geometrifying Trigonometry. We will write LAAZ and LEEZ only, and then we will generate the permutation and the Cartesian products generations for all these cases. It says it has found the 32 variations and 16 variations for the cos square theta and 16 variations for the sine square theta. And if we select all and then load all these selected, then on the panel we can see the outputs of these GT simplexes. And when we will change the theta, that means for the different value of the theta we have to construct 32 tracing papers, and we have to stack all these 32 tracing papers one after another to understand these kind of geometries. And in Sanjoy Nath'S Geometrifying Trigonometry Simulator we can do these things very easily, such that in the Pythagoras theorems, and if we want to simulate for all these varieties of 32 stacked tracing papers, then for every angle we have to construct 32 well designed tracing papers, and we have to stack all of these tracing papers one above another aligned with the common L, the common line segments. Then only we can visualize all these kind of pictures, and these kind of pictures are very much useful for the crystallography things, for the origami kind of things, and these are also applicable for the tensegrity, the truss designing, for the free body diagram designing, for the product designing, for the many kind of products. And these product designing systems are directly related to this Sanjoy Nath'S Geometrifying Trigonometry, and it has a huge application in the modern times. Thank you.